Hello students, welcome back. Let us resume our discussion in section 2. And previously we went through the intersections. The intersection of all subgroups. Intersection of any collection of subgroups is again a subgroup. And is the largest subgroup contained in all those members of that collection. But then again, if that collection happens to be the set of all subgroups containing a certain starting set S, which we're going to call the generating set, in that regard, the intersection is the smallest subgroup that contains the set S. We went through all that. Now, let's start from this generating set S. Let G be a group, and let AI be members of G for all I. That's going to 1, 2, 3, 4, possibly for the infinity or more, because this capital I is arbitrary index. The smallest subgroup of G that contains all AIs is called the subgroup generated by AIs, and we use this notation. If we had just one element here, then it is a cyclic subgroup generated by that one element. But here we are considering two or more, possibly infinitely many. And we use the intersection here, so the existence and uniqueness is always guaranteed. We established already. And then alternatively, instead of considering all those elements directly, you can form a subset S of G by taking all those AIs together and forming a set, and then consider a subgroup generated by this set S, as we did previously. You can do that too, but then again, the trade-off is you're introducing an extra character S, so it's a bit confusing. I didn't like that, so I just started from the elements, but it's the same idea. So this is well defined. It does exist and it's always unique or good. But then again, I'd like to go one step further. What's the property here? It turns out this subgroup consists of all those sequences of this form, which we call the words made out of the finite arrangements of alphabet AIs. AI1 to the K1 power, AI to the K2 power, AI3 to the K3 power, all the way over to AIN to Kn power, and n can be arbitrary. Could be just 1, or could be 15, or could be 5,000 or whatever. As long as it is finite, it's okay. And then the powers can be arbitrary integers. If you have 0, then it's the identity, so it's easy. And if it is positive, that means repeated group operation of that AI. And then if that's negative, that means repeated operation of the inverse of AI. Exactly the same notation that we had been using for cyclic groups. But then again, this AI1, AI2, AI3, there are multiple of those. So things are far more complicated than cyclic groups. One more note, these AIs need not be distinct. So AI1 could be A14, and AI2 could be A17, and AI3 can be A14 again, and AI4 can be A2, kind of like that. And then in the end, AI 5000 could be A14 again, whatever, and then all those powers. And then the word expression need not be unique. You see, this expression and some other expression may end up being the same. For example, do you remember dihedral group? Something like that. So if you switch the order and then you get something else, and then that'll of course change those powers and orders, but it can simplify things. And then of course, if you have an abelian group, yeah, a dihedral group was a bit too complicated. Abelian would have been a lot better. That even if you have just 15 generators, A1 through A15, but this could go on 5,000. But then again, you can always switch the order and then simplify, so you can go back to at most 15 of those. So word expression need not be unique, and the selection of those need not be distinct. Pretty much anything that you can think of is all allowed, basically. And we can prove that that kind of thing forms a group. Yes, we can prove that it satisfies all those three, close under the group operation, the identity, inverse, everything. And not only that, it's the same as the previous expression. So this expression and that expression are the same, as we're going to prove later. And either way, we get a certain group, a subgroup, generated by all those AIs. Now, in a special case, if this subgroup generates entire G, we're going to call AIs the generators of G, and we'll say AIs generate G. And then the set of all those generators is called the generating set. Yeah, this set S, that's a generating set. And if the set is finite, then we can say G is finitely generated. The generating set may not be unique. So in some cases finite, in some other cases infinite. If the finite generators exist, if a finite generating set exists, then that's enough to say G is finitely generated. Okay. So we covered all the lingos, and then this one, and then the property of that one, yeah, we discussed. The only thing that we didn't cover is this. They actually are the same. How do you prove that? Well, we're going to prove through set inclusion. This is a subset, and then that is a subset, so that they're equal to each other. Let's make this observation first. Because the intersection is a subgroup, it's closed under the group operations. So all AI1, AI2, all the way AIN, they all belong to the intersection because each of those belongs to any subgroup H of G that includes all AIs, you see. So each of these belong to the intersection. So any K power belongs to the intersection. And then any multiplication of those belong to the intersection as well, because this intersection is a subgroup. It's closed under the group operation. As a result, the arbitrary expression here belongs to the intersection. Consequently, this word expression here is a subset of the intersection expression. So this expression here is a subset of the intersection expression. Okay, we are done with one set inclusion. Let's prove the other way around. Next, we're going to prove that this word expression here is a subgroup. Well, it's closed under multiplication because if you have certain elements like this, AI1, K1, AI2, K2 power, and so on, to the Kmth power, and then AJ1 to L1 power, all the way to AJ into Ln power. But then again, we still have a long word of length m plus n. So yes, it belongs here as well. So closed under the group operation. And it has the identity, 0 power, and that's it. and it also has the inverse. If you apply the inverse formula, then negative power is distributed, but in reverse order. So negative kn power and the negative km power all the way up to negative k1 power, like that, in reverse order. But still, it's a repetition of the sequence, so it belongs to that set of all the words. So this is a subgroup, and therefore it includes the smallest subgroup. So the intersection is included in this set of all the words as well. So we have both inclusions. One is subset of the other, and the other is a subset of the first. So they must be the same. Conclusion: all these expressions are the same. So the subgroup generated by A1, A2, A3, and so on can be considered as the intersection of all subgroups that include all those AIs. Consequently, the smallest subgroup including all those AIs. Also, on another viewpoint, is the set of all words made out of these alphabets, A1 through all the AIs. Yeah, A1, A2, A3, and so on, possibly infinitely long. Okay, all right. We established the concept of generating set and finitely generated. Now let's consider finitely generated abelian groups. Up to this point, we consider G as just arbitrary group, possibly non-abelian, but let's stick to abelian groups. In that case, this wording is going to be much simpler because we can always change the order. So if you have, say, 3 generators, then you just have A1 to whatever power, A2 to the whatever power, A3 to the whatever power, and that's it. Even if you have some more duplicate, I can always change the order and simplify. As a result, we get much simpler result as this, called the fundamental theorem of finitely generated abelian groups, where the fundamental theorem of abelian groups, I'm not completely sure how it is called. I think it should be called the fundamental theorem of finitely generated abelian groups. There are many fundamental theorems out there, so anyway, as the name suggests, the proof is going to be really hard. Yeah, it's a fundamental theorem, so what do you expect? So we're not going to cover it here in Abstract Algebra 1. It does appear in our textbook, but I'm not going to cover it. Maybe we'll do that in Abstract Algebra 2 if I have chance to offer it, but not here. Let's just go to the conclusion. Every finitely generated abelian group is isomorphic to this form, Z P1 to the R1 power, where P1 is a prime number, and Z P2 to the R2 power, all the way over to Pn to the Rn power, and those are all finite. And then times Z times Z times Z times whatever, and that part is infinite. Number of Z's here is called Betti number, and all those, the finite part, those are all unique. And we're going to study some example problems associated with this in a separate video. For now, we'll get just satisfied with this description. No proof.